What's up, everybody? Welcome to another lecture in our Chemistry States of Matter unit. This is going to be the second lecture about phase changes and a little bit of the math and energy involved in phase changes. But I don't want to spend too much time here on the title screen, and so let's move on to the first slide. So phase changes are a phase change, a change between phase. All right, we're going to first start talking about melting and freezing. All right, the melting point is the temperature at which something goes from a solid to a liquid, the temperature at which something melts. All right, it is the same exact temperature as the freezing point, which would be going from a liquid to solid. In melting, we have to think about what we have there. We have a solid. The molecules are tightly packed together. Because they are very packed together, they are held together by intermolecular forces. All right, those London dispersion forces, dipole-dipole forces, and hydrogen bonds that we talked about last time, all right, are all involved in solids. As energy gets absorbed, and usually we do this through heating, the substance starts to heat up. We don't have to actively heat it on a stove or anything. If you take an ice cube and set it on the counter, it's going to melt. Well, it's going to heat up just from the ambient temperature of the air. So what we have going on is energy gets absorbed, and these IMFs start to weaken. And as the IMFs start to weaken, the molecules are able to move more freely. Eventually, those molecules can move past each other, all right? But there are still IMFs holding the molecules together, and this is what we would call a liquid. So the liquid, the IMFs are there, and they're between the phases, or between the molecules, but they do allow for the molecules to move freely around each other, and they can be broken and reform a little easier than they can in a solid. In freezing is the opposite of melting, so energy gets released and IMFs are formed and hold the molecules together in a more rigid fashion until we get a solid again. Another way we can look at the phase change of melting, all right, is to look at it quantitatively or with numbers. All right, and to do that, we need something called the heat of fusion. What the heat of fusion is the heat required, or the energy required, to melt 1 gram of a substance at its melting point. The heat of fusion itself, we are looking for Q, which is energy, or specifically heat energy. The M is the mass, and H fuss stands for heat of fusion. Now, there's no increase in temperature when a substance is melting. All the energy is going into breaking those IMFs. Now, let's do an example. How much energy is needed to melt 25 grams of ice, and I have the heat of fusion? Well, I'm going to use the formula Q equals mass times the heat of fusion, or energy is the mass times the heat of fusion. I have 25 grams of ice. There's my mass. I know it's mass because it's grams, so I'm going to plug that in, my 25.0 grams. And then my heat of fusion is 334 joules per gram. And this will let me cancel out those grams. Now I just type this into a handy-dandy calculating device. 25.0 times 334. And what I end up with is 8,350 joules, which is the unit of energy. Or if I wanted to be fancy, 8.35 kilojoules, where a kilojoule is 1,000 joules. Either unit would be fine for an answer to a question like this, because it doesn't ask me what unit to have at the end. I would have probably just kept it as joules. Why do more work and possibly mess up a conversion? even if it is an easy conversion like going from a standard unit to kilo. That's how we do a heat of fusion question, a melting question. How much energy is needed to melt something? You will always be given the heat of fusion, or at least be given a way to look it up. And the mass, if you don't have the mass, but you have a sample in front of you, you can just stick it on a balance and find out the mass pretty easy. So it's not that hard. It's one simple multiplication. Let's move on. Next up is the boiling point, or vaporization. Now this happens when the KE, or kinetic energy of the liquid, overcomes the pressure of the air and forms bubbles of gas. All right, so what this means is that the liquid eventually changes to a gas. All right, boiling point is a function of atmospheric pressure. That means the more pressure there is, the harder it will be for something to boil. All right, so pressure affects at what temperature something will boil. Water boils at a lower temperature in Denver, Colorado, because it is higher up than it is here in Rochester, New York. And because it's higher up, there's less air pressure, so just there's less stuff pushing on the liquid, kind of condensing it into a liquid. What's actually going on here at the molecular level is, again, energy is absorbed and breaks those IMFs to the point where the molecules can just move around the entire container. All right? It's not that there are no IMFs in gases, just they are really, really weak compared to that of liquids, and especially compared to that of solids. And then every now and then you might have heard the term volatile liquid. A volatile liquid is just a liquid that will boil at a low temperature and will evaporate readily at room temperature. So this would be something like rubbing alcohol or gasoline. The opposite of boiling or vaporization is condensation. In this case, the gases have to be cooled. And what this does is this reduces the kinetic energy, and it makes sure the molecules are close enough for dispersion forces and IMFs to form. All right? And the molecules start to stick together. The other way we can cause something to condense, though, is we can compress it. All right? And this can push the molecules close enough for those IMFs to form. This is a form of increasing pressure. There is a special temperature called the critical temperature, and we'll see this more later on in the unit. But above the critical temperature, no amount of pressure will condense a gas. So it's kind of a unique temperature for every substance. And then there's a critical pressure as well. The critical pressure is the pressure that it would take to condense a gas at its critical temperature. Now we're going to take a look at a very similar formula to that heat of fusion formula. This is the heat of vaporization formula. Heat of vaporization is given the symbol HVAP. All right, and it's the heat required to vaporize a gram of a substance. It is almost the exact same formula. You got your Q for your energy, your M for your mass, and instead of HFUS for heat of fusion that we see when melting, we have HVAP, the heat of vaporization. And again, there's no increase in temperature when a substance is boiling. All right, phase changes happen at a constant temperature because all the energy is going into the substance, changing phase, breaking these intermolecular forces. Whereas when you are not changing phase, all the energy is going into heating up or speeding up all the molecules. So, we're going to take a look at how much energy is needed to melt 18 grams of ice. And I have a heat of vaporization of 2,258 joules per gram. To do this, I'm going to write my formula. Q equals mass times heat of vaporization, mHVAP. I'm then going to start plugging things in. I have 18.0 grams of ice. There's my mass. So Q, or energy, is 18.0 grams times the heat of vaporization, which up in the question is 2,258 joules per gram. Again, this is something you'll either be able to look up or be given. All right. Happily enough, the grams, once again, are going to cancel out. And I just do the simple multiplication. I take 18.0, type it into my handy-dandy calculating device, multiply it by 2,258, I get 40,644 joules. Or if I wanted to put it into kilojoules, I would divide this number by 1,000. I'd get 40.644 kilojoules. I could make a couple extra changes here to stick with sig figs, but we're just kind of going to keep it right here to keep this nice and short. So that's all we have. Those are the two formulas so far in this unit. MHVAP and MHFUS, depending on whether you have melting or freezing. It's just knowing which one to use when, and shockingly enough, HVAP stands for vaporization, which also starts with VAP. It's not confusing like HFUS for fusion, which does not look to correspond with melting, until you find out that melting is sometimes, referred to as molecular fusion, but it's kind of different than nuclear fusion, and so nobody ever uses it, and whatever. We're going to just ignore that part. HVAP for vaporization or boiling, HFUS for melting. And that is it. Have a good one. Ask me questions if you have them, if you can get a hold of me, because I'm your teacher, or ask whoever your teacher is if you are somebody out there that stumbled across this video thing. Bye.